Okay, so once again, good evening. You are welcome to the last day of this training. So tonight we are going to be looking at advanced statistical modeling in R. Advanced statistical modeling in R. So under this, we are going to be checking the regression techniques and the time series analysis. Both of them are statistical tools which fall under the inferential statistics in R. So, and it's one of the advanced statistics that we have. One of the advanced statistics that we have that majorly in all field, they make use of these models, the regression model, the time series model, they make use of them in all field. Name it, is it medicine, is it agriculture, is it engineering, name that field. You will see them using regression techniques or time series analysis. So tonight we are going to be checking those statistical tools this tonight. Objective of this course. What is the objective? What you are expected to cover in tonight's course? Number one, understanding the key regression techniques. When we are talking about the regression, oh, you have to understand what we mean by the regression. Then, what type of regression do we have? Is it simple linear regression? What is simple linear regression? When do we use simple linear regression? So we're going to be checking that tonight. Is it multiple linear regression? When do we use multiple linear regression? We're still going to be checking that tonight. Is it logistic regression? When are we going to be using that? When you see a particular data set, to be able to know whether you are going to use a linear regression or more multiple linear regression or logistic regression, you should be able to do that. So after this class, you should be able to perform those analysis. Number two is that you are going to gain proficiency in R. We started that before, but I've not shown us how we use model in R. So we're going to be seeing that tonight, how you can use statistical model in R. But in building models in R, the one that we're going to be checking tonight is going to be an existing model. So if you want to build a model in R, you will need the knowledge called a machine learning. So we normally use most of the data that we normally have in the real world, the large data set, we normally build a model for them. So in the course of building the model, then we land ourselves in what we call the machine learning. But we're going to be making use of the models, the existing one, like the logistic regression model, like the linear regression model, like the time series. Under the time series, we have a lot of models under the time series. Is it autoregressive model? Is it autoregressive moving average model? Is it autoregressive integrating moving average model? Is it seasonal moving average model? We have several models under what? Under the time series analysis. So we're going to be checking them tonight. So also at the end, what we need to cover tonight again is the learning basic analysis forecasting. Learning basic analysis and forecasting time series data. Oh, after we have developed a model, the essence of every model, please note this tonight, the essence of every model is for us to forecast. It's either we do the classification or we forecast. What did I mean by that? So when you're talking about the classification, oh, let's say for instance now, I want to develop a model that can dictate whether someone will have the diabetes or not. So in that case, we normally use what we call a classification. It's either they have the diabetes or not. So that is what we call the classification model. But if I still move further now, okay, I want to check a model that I can use to predict. Give me some factors. Give me the diet. Give me the blood. Give me the glucose level in the blood. Give me the BMI and some other factor. I will be able to predict whether someone is going to develop a diabetes. So that is what we call the forecast. We want to predict ahead. So enable, but tonight you should be able to. We are going to be checking to enable us to exploit model forecasting time series data using tools such as the forecasting package. There is what we call a forecasting package in R. So and build data set in R. So these three things we're going to be covering tonight. So that is going to be the end of our camp. Why do you need this? You may ask yourself, Why did I need to attend tonight's class? Number one, data-driven decision making. In this era now that we are, there's no sector that they don't make use of data. Ability for you and I to use a statistical model or to use the machine learning model to do some data analysis and bring out meaningful information for future decision making is going to help our society at large. Another one is demand for analytical skills. The skill of data analysis now is now going to is increasing every day. Every day. If you see any job adverts now, they will tell you that either you have the knowledge of R or you have the knowledge of Python. They will ask you for one analytical skills. So the knowledge that you are going to be gaining here tonight, it is not only for you alone, but it is for your place of work, it is for your research, and it is for all people that surround you that you can help in analyzing their data or in analyzing their research work for them. So that is what we call the analytical skill. Another thing that the reason why you still need this class is effective problem solving. By learning to apply R to practical problem, participants gain the ability to analyze the relationship between variables. Now, let's say, for instance, now I have the height and weight. I want to analyze, is there any relationship between the height and the weight? So with the knowledge of regression, I can check whether the relationship between there's a relationship between the height and weight. Okay, I've established that there is a relationship between the height and the weight. What type of relationship? Is it a negative relationship? Is it a positive relationship? What did I mean by the positive relationship? The positive relationship simply means that as the height is increases, the weight also increase. That is what we call the positive relationship. But when you are hearing the negative relationship, that means that as the stock exchange is increasing, the number of demand is decreasing. So that is what we call the negative relationship. So by using simple linear regression, the knowledge of simple linear regression can undo that. And when we're talking about the multiple linear regression, that means that you are considering a variable that is more than two. That is more than two. So those are the things that we're going to be checking tonight. At the end of this class, you should be able to perform the following. At the end of this class, perform regression analysis, apply simple multiple model using ML. ML simply means linear model. Anytime you are seeing the word ML, ML is the package that we normally use in R to perform a regression, whether it is linear regression or it is multiple linear regression. And then when we're talking about the linear relationship, when we're talking about the linear relationship, that means that the relationship between Mr. A and Mr. B is not what it is directly proportional. It is directly proportional, so it's not inverse. That's what I mean by the linear. So from our variation, so it's directly proportional. So maybe when the Mr. A is increasing, Mr. B is also increased. So, but it is in linear form. Is in what? Is in linear form. So we're going to be checking. You should be able to do that at the end of this class. Then build and evaluate logistic regression model. You've heard about logistic regression. What is the logistic regression? Let me quickly do the recap before we move down to our work for tonight. Logistic regression simply means that the dependent variable, by now we should know the dependent variable. Your dependent variable, which is also the outcome variable or response variable, the outcome is binary, is dichotomous, is polar. That is either yes or no, is either pass or fail, is either the disease is present or not. So in that case, when you have your dependent variable that is dichotomous, and then you have several independent variable, or you have one independent variable, in that scenario, you can no longer use a linear regression, neither you will use multiple regression, but you will use what we call logistics regression. But in the case of the linear, your dependent variable will be what? Will be numeric. Your dependent variable will be numeric. But in the case of logistic regression, your dependent variable will be categorical. So, and lastly, analyze and forecast time series data. So, utilizing our forecast package to analyze trend, we're going to be checking what they mean by trend tonight. Trend, then the seasonal pattern. Because in time series data deals with time. Let's say, for instance, now we want to study the number of students being admitted for the past 10 years. For the postgraduate, the number of students being admitted for the past 10 years. So that means that we are going to work back to 10 years, and that is we're going to start from 2014, so 2015, 2016 up to 2024. So in that case, we are going to check the trend there. Means that is it the number that they are admitted every year, is it increasing over time or decreasing over time? And the seasonal pattern means that, oh, maybe from what's it called, maybe a particular season, let's say a particular season, maybe after the strike, maybe ASU went for like 6 months or 8 months strike. So after the strike, we discover that when they bring out the when they bring out the admission, sorry, the form for the admission, we discover that we have a lot of people. Why? What really happened at that moment? Maybe for over the years that the ASU has went on strike, people have been packing up, different set has been graduating, and they want to come for postgraduate, but there is no space because of the ASU. So by the time they now open the space, you will discover that we have a lot of people applying. So in that case, that is what we call the season. A lot of things has happened in that season that make that increment. So we normally use time series to check that. Then we are going to be checking the residual. Another name for residual is the error. So we're going to be checking the residual in time series data analysis and make accurate forecasting. Because if your error is not properly treated, it will give you the wrong forecast. You are going to have a wrong model. And once you have the wrong model, what you are going to be predicting will not be correct. So those are the things that you should do at the end of this class. So let's move. Now we move to the regression. Then we're going to start by linear regression. What is a linear regression? Regression is not something that is strange to us, but if you are the one that you are hearing for the first time, you can still move on with us. What is a linear regression? Linear regression is a statistical technique used to model the relationship between dependent variable or response variable. Another name for dependent variable, you see a response variable, and one or more independent variable. When you have more than one independent variable, it is called a what's it called? The independent variable is also called a predictor. Another name for independent variable is what we call the explanatory variable. Another name for independent variable is what we call the treatment. For those people in College of Medicine or Public Health, it is called what? Treatment. Now, it's assumed linear relationship between the dependent variable and then the independent variable. So anytime you have a linear relationship, for instance, now y is equals to x, so that one is linear relationship. Y is equals to x, that one is a what? Is a linear relationship. But when you have y is equals to 1 over x, it's no longer what? A linear relationship. When you have y is equals to 1 over x, it's no longer a what? A linear relationship. Now, type of linear regression. We have two types of linear regression. Number one is simple linear regression. Why did they call it simple? Why did they use that word simple? It simply means that you only have one dependent variable and one independent variable. When you have one independent variable and one dependent variable, it is called a simple linear regression. Let's say, for instance, now, your monthly income and your total savings. So if you want to find the relationship between your savings and your monthly income, you may want to use, okay, over the 5 years I've been saving and I've been receiving this income. Let me check what is the relationship between them. So in that case, if you want to model that, we normally use what we call a simple linear regression. So another one that we're going to, which is the number 2 of the linear regression, is what we call the multiple regression, from the word multiple. So that means that you have just one dependent variable, which is the variable y, and then we have multiple, more than what? 2 or more than independent variable, yes. So that means that if I want to measure the obesity is the dependent variable. I want to measure it over the diet, the exercise, then the number, the sleeping hour. We have more than one independent variable like that. So immediately you have 2 or more independent variable. You can no longer use what we call the simple linear regression, but we're going to use what we call the multiple linear regression, because we have more than one independent variable. Another regression that we're going to be checking tonight is what we call the logistic regression. It's what we call the logistic regression. Unlike the simple linear regression and the multiple linear regression, or generally, unlike the what? Unlike the linear regression, logistic regression is different from them. Why? Because the dependent variable of the logistic regression is a what? Is a polar, is a dichotomous, is a binary. So that means that if you're having your dependent variable to be binary, yes or no, success or failure, disease or no disease, and you want to measure it over other factor. Let's say, for instance, now you want to measure it over socio-demographic factor. That means that you are going to use what we call a logistic regression. So that means that you are going to use what we call a logistic regression, or you want to check some factors that contribute to the HIV status. Remember that the HIV status is either positive or negative. In that case, the HIV status is the outcome. So the outcome now is a polar, is a binary. So that means that if you want to use that, you are going to use what we call a logistic regression. Let's say, for instance, that for those people in education, if you want to measure the whether some student will pass the English, is either they pass it or they fail it. So the outcome is them passing the English or failing the English. So then measuring it with other independent variable. Independent variable are okay, the number of hours that they spend in reading the English, the number of literature that they've read, the number of what's it called, the number of lecturers taking them. Those are the independent variable that you want to check on the outcome of them being passed or not. So in that case, we are going to use what we call a logistic regression. A logistic regression is a powerful tool. Is a powerful tool in the family of what was it called, generalized linear model. We only call them GLM. GLM is their family. In GLM, you can have the what? You can have logistic regression. You can have a Poisson regression. You can have the binomial regression. There is the same thing as the logistic regression, because the binomial by means two. So we are talking about binomial. It means that you have two responses. So they put that one inside the logistic regression. So in the family of generalized linear model, GLM, maybe you have been hearing GLM before. It is called generalized linear model. In that family of GLM, we have a lot of model. We have the Poisson model, we have the logistic model, we have the negative binomial model, then we have several other models in the family of what? In the family of GLM, generalized linear model. When to use the logistic regression? I've explained that the dependent variable is categorical. That is very, very important. Once your dependent variable is not categorical, don't go and think of what? Don't go and think of logistic regression. And then at the end of this class, any paper that you are picking, you should be able to identify the statistical method that they use there. You should be able to know whether the statistical method that they use in that paper is right or wrong. And for those people that is writing project, you should be able to use a correct statistical tools, a correct statistical model for your what? For your project. And those people that is in research institute, once they bring a particular, let's say for instance, now they want to find out whether a particular plant will survive. For those people in horticulture, if they want to know whether the particular plant is going to survive or not, you should be able to model using a logistic regression to determine the survival rate. Oh, this one is going to survive. What is the order of them, or what is the order of these plants being survived? So you should be able to do that using a logistic regression. Then the goal is to estimate the probability. This is the goal of logistic regression. The goal is to estimate the probability that a given observation belongs to one of the two categories. Is either it is going to survive or no. We don't have the third one. Then the logistic regression model predict the probability of the dependent variable. Let's say the y. Y is equal to 1 means that that particular plant will survive. So anytime your y is equals to 0, that means that that particular plant or we know what will not survive. Or you want to check the what's it called, whether a particular female is going to develop a what's called a cancer, or they want to develop a particular disease. We use logistic regression to do that. And another thing that we normally use logistic regression to do in the aspect of the machine learning is that we normally use logistic regression to screen out some variable that is of importance. Not every variable that you can use to build a model. How do you know whether this particular variable that I want to use to build my model is statistically significant, or is contributing good thing to is going to contribute a good thing to my model? We still use logistic regression to screen our variable. That one is when you are developing a model, or you have a large data set that you are working with. Now, after this, there is what we call model evaluation. Everything that we're going to be doing tonight is about model, because we've talked about how you can use your tools using different statistical method. We've talked about the SPSS, how you can use SPSS, Stata, Excel. Okay, after you've done the analysis, you have your model. How do you evaluate your model? How do you know that whether your model is good or not? How do you know that whether your model is consistent? How do you know the accuracy of your model? How do you know whether the prediction of your model is robust? So we normally use the metrics for model evaluation. Model evaluation is the process of assessing how well a statistical or machine learning model perform in predicting or explaining the outcome. That is what we call the model evaluation. If you want to know whether the independent variable that you have, they are really performing well by predicting your outcome. I don't know, maybe you've heard about the R square before. The R square, the adjusted R square. What simply means that R square is just that we want to know the amount of variation that your independent variable can predict for your outcome variable. So R square is one of the model metrics. We're going to get there now. What is the goal of model evaluation? Number one, accuracy. Measure how well the model predict the outcome. I've mentioned it. That is number one goal of model evaluation. Any model that you are using or you are developing or you've developed, you must be able to tell us how you evaluate it, so that before you can recommend it. So in the course of your evaluating of the model, we are going to know whether this model worth to be used or not, whether this model is worth to be used or not. So model evaluation is very, very important. Another one is generalizability. So we can assess how the model perform on unseen data. That is why there is a part of machine learning that we call the training and then the test. When you have all the data and you want to use it to build a model, we normally use it in machine learning. We're going to divide that model into two parts. We're going to use 70% to train the model. The reason why we are training the model is that we want to fill the model with the 70% of the data. So immediately we fill the model with the 70% of the data, they will now use 30% to test it and see whether it's going to perform better. Let's say, for instance, now, if you notice, let me give the example that is common between us. Your apps that you normally use on phone, if you open, let's say, for instance, that you want to open a particular app and you open the page that contain all the apps, you will see that it's going to give you the most useful app. So that means that the model, the AI of that phone that they've configured, it has studied you over the time. That the process of study is that it's studying the data, it's studying the apps that you are pressing always. Maybe when you open your phone, and the first thing that you're going to press is your WhatsApp. Maybe when you open your phone and the first thing that you're going to press is your Facebook. When you open your phone and let's say the first thing that you're going to press is your message. So it will come to a point whereby when you open down your phone, the message will be number one. So over the time, the AI that they use to configure that phone, it has studied your data, your movement on that apps over the time. So it can tell you, okay, let's say for instance, now you can just, can you guess the app that I will open? It will be the one to tell you that I have 90% sure or 95% guarantee that when you open your phone, it is WhatsApp that you are going to click. Why? Because over the time you have studied that when you open your phone, you are you go straight to the WhatsApp. That is what we call the model training. That is how they train the model. So in the course of you developing your own model, you are going to use 70% to train it, while you are going to use 30% to test it. So by that time, you cannot generalize that, based on my based on the metrics or the model evaluation, I am 95% guarantee that if you use this model with any data that relates to this, is going to give us a better precision. So that is what I mean by that. Then the assumption validation. We normally use model evaluation to check whether you don't violate some assumption. There are a lot of assumptions. Every model has its own assumption. Once the assumption of a particular model is violated, that means that the level of precision will be low. That means that the accuracy will not be achieved. That means that the level of the robustness of that model will not be achieved. So it is very, very important to do model evaluation. And then another one is comparing models. You may want to compare, okay, let's say for instance that you have developed a particular model in Nigeria here, another person has developed his own in India, another person has developed their own in, let's say in Portugal, and you want to check whether the same model can perform in those areas. Then we use what we call the model evaluation. If I have my model evaluation here in Nigeria and my model evaluation is telling me that it is 95%, let them do their own model evaluation in UK and let us see whether it's going to be 95%. Let them do their own model, the model evaluation in Portugal, and let us see. So by the time you have that comparison in model using the model evaluation, we cannot generalize that, oh, take this model to any country, is going to do what is going to perform better. That's why we have a room for what we call the multinational, what's it called, multinational training, multinational experiment. Multinational experiment. That's okay. They are performing the same experiment in Ghana. They are performing the same experiment is being performed in Nigeria. The same experiment is being performed in Egypt. At the end of the day, we use model evaluation, some metrics to check whether they are going to arrive at the same thing. So the model evaluation is as important as anything. Now, let us now take it one after the other. Model evaluation. When you have a linear regression, how do you do a model evaluation for linear regression so that you will not be using model evaluation for linear regression of time series for linear regression? You should know the right model to use. Number one, for linear regression, for regression model generally, number one is we use R square. I've mentioned the other time, we use R square, proportion of variance in the dependent variable explained by the model. Let's say, for instance, now, if I have my R square to be equals to 80%, it's measured in percentage, although the value is from 0 to 1, but we multiply it by what? By 100 to have a what? To have a percentage. So let's say, for instance, I have my R square to be 80%. What is the interpretation of that? It's telling me that out of the total variability in my dependent variable, which is y, x, which is my independent variable, can only account for 80% of it. Let me take it again. If you have your R squared to be equal to 80, it means that out of the total variability in my dependent variable, my independent variable can only account for 80%. The remaining 20% can only be accounted for other variables that is not in that model. Maybe there are some other variable that is supposed to add to your independent variable that it is not there. That is why we have the room for that 20%. So, but the 80% that you are seeing, that it means that your independent variable can only account for 80% out of 100% total variability that we have in your dependent variable. So that is why we normally use a matrix R square into what to do the measurement, to do the model evaluation for the what? For the regression. For the regression. So okay. Do you have a question?
Yes, sir. Please. Yes, sir. Please kindly take that again.
Which one should I take again?
The R square equals to 80%.
Okay, thank you. I will do that now. Now, okay. When you have your R squared to be equals to 80%, what is the interpretation? Now, the total percentage is 100. Then we have the total variability is also 100. And the variability is measured in your dependent variable, which is your y. So what that one means is that out of the total variation that we have in our dependent variable, which is y, your independent variable, which is x or x's for multiple regression, can only account for 80% of it. The remaining 20% is being accounted for some variable that is not in your model. Other variables, other contribution, other factor that is not in your model is what is contributing to that 20%. Let's say, for instance, now you have a model for obesity, obese and the exercise. Now, if you do a simple linear regression and you have your R squared to be equals to what? To be equals to 80. So that means that the exercise can only account for all the variabilities that cause obese. And your R squared, your exercise can only account for 80. Well, let's say, for instance, that you add another variable called the diet that you are taking. So by the time you still do the R square, maybe the R square has increased to 85. So that means that the 5%, the contribution of 5% is the presence of the diet that you added. If you had another one now, okay, let's say for instance now the length of sleeping, if you still add it to that model, you will see that your R square will keep on increasing. But immediately you add another variable to your R square and you see that your R square decreases, that means that that variable is not contributing good to that model. You remove it. That is why we normally test. We normally test model. So you put one variable, you will see you check the model evaluation. Is it increasing or decreasing? If it is decreasing, you remove that variable straight. You add another variable. So because we need those variables that can give you the higher level of precision, But if there is no presence of the model metrics or the model evaluation like the R square, we may not know. We'll just be putting all those independent variables in our model. We'll just be putting it there. You will not know whether the model is performing better or it is not performing better. I hope I have answered your question before we move on.
Yes, sir. Thank you very much.
All right, you are welcome. So let's continue. Okay, so then we have what we call the adjusted R square. Adjusted R square. You let me explain it in a layman language that you will understand. You know, we have the general name for our petrol, diesel, and the like. We call them crude oil. We call them crude oil. They are unrefined. It is when you now refine it that you are going to have what we are going to have what we call the petrol, the kerosene, and then the like, based on their is it their octane number or something like that. Now, the R square is the raw, is the crude. Let me put it like that. Then the adjusted R square is the refined one. So that means that the R square that you are seeing there is there are errors. There are errors. We call it is it volatile in crude oil? There are errors. There are some errors that is still embedded in the R square. So that is why if you have your output, maybe you are performing analysis and you have your output, you see R square, you see adjusted R square. Please interpret the adjusted R square. Adjusted R square is the refined one. That means that they've considered the error, they've removed all the possible noises that you may find in your model. So another name for error is noise. When you hear the word noise. So that means that you take care of the noise. The term noise we normally use this in time series. So that means that you take care of your noise. So immediately you take care of that noise. So that means that you now have what we call the adjusted R square. So you are going to interpret the adjusted R square, but there won't be the adjusted R square without the existence of R square. You cannot have your petrol or your kerosene without the existence of crude oil. So that means that the crude oil have to exist before you have your petrol. That means that your R square have to exist before you have your adjusted R square. So that is also for that. There is another one what we call the mean root square, the mean square error, MSE. The mean square error. What did they mean by the mean square error? Why do we use mean square error? Now, the mean square error simply means that, by the time you find your model, you filtered your model, then you now want to predict. So now the difference between your observation, the observation are the data that you have initially. Then now, after you've developed your model, you want to predict some observation too. Remember that you have the initial observation that you used to build the model. Now, after you've built the model with those data, now you want to predict. Now, the difference between your original observation and then the predictive one is what we call the error. The error. So by the time you square it, it is called the square of error. Please take it. Let's just take it one by one like that. The difference between the two is what we call the error, the predictive and the observation data. So the different means minus. So it's what we call the error. Now, by the time you square it, is what we call the square error. In your analysis of variance ANOVA, we normally hear sum of square error. That is how they got it. Sum of square error. That is how they do what they got that. Now, by the time you now find the mean of the square error, that is what we call the mean square error. The mean square error. Now, there is another one called root mean square error. After you've gotten your mean square error, you take the square root. The square root of that is what we call the root mean square error. Root mean square error. Those are metrics that we normally use in what? In evaluating our regression model. Another one is what we call the mean absolute error. After you find your what? Your error by what? Observation, the observation minus the predicted model. So the difference between the two. Then you now take the absolute. The reason why we are the essence of taking absolute is that if you have any negative, it's going to normalize it. Once you put absolute value, the absolute change the negative to positive. The absolute change the negative to what? To positive. So you can now find the what? The mean. Now, another one that we have is what we call the Akaike information criteria, AIC. Akaike information criteria is one of the method that we normally use, one of the useful metrics that we normally use to check two models. Let's say, for instance, now they've developed one model in South Africa, and you yourself, you develop another model in Nigeria. If you want to check the one that perform best, we normally use Akaike information criteria or a Bayesian information criteria. Now, the model that with the highest value of Akaike information criteria, the AIC, or the one with the Bayesian information criteria, BIC, is the what? Is the best model or the better model. Let's say you have like 10 models. Once you check their AIC or you check their BIC, the value of their AIC, the one with the highest value of the AIC and the one with the highest value of the BIC is the best model or the better model, so that you not go and present that it is a best. There is no best model, but we normally have a better model. So it's a what? Is a better model. So let's continue. Do you have any question, please, before we move on? Because tonight's one is going to be loaded a bit. Any question before we move on? Can you still hear me, please? Okay.
Yes, sir. Yes,
Mr.
sir.
Ride,
Please.
go ahead.
Okay,
Let's Mr.
sir.
Ride
I,
ask first. So please go ahead.
I have some few questions. I was only waiting till till I
Okay,
think
so
8
I don't
when
want
you
us to,
would
to
officially.
compile it. So let us be taking it like that. Oh, yeah, I'm listening to
Ah,
your question.
I don't I don't even know where to. But okay, so what's the difference between correlation and simple linear regression? I didn't want to stop you when you were there when you were trying to explain simple linear regression. So what's the difference between correlation and simple linear regression? I think it's close. So what's the differences, sir?
Okay, let me quickly answer that. Remember that I made mention something yesterday that so far that two variables are correlated, that does not mean causality. Now, correlation is just to let us know the strength, and then after the strength, the direction of the two variable. But you cannot use a correlation to predict. No, 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 no. Correlation cannot tell you the prediction. You cannot use correlation to model. You cannot use correlation to model. It's just telling us the strength of association, and then the direction. That is the work of correlation. But when you are talking about the regression, whether it is simple or linear, we normal it's a model. Regression is a model. The simple linear regression is a model. Correlation is not a model. So that is the difference between the two. Please ask the other question. Are you clear with that, or I should explain again?
Yes, I'm clear, sir. I would retain it to the end of the class. Let's continue so that we don't digress so much, sir.
Okay, Madam Ebong, am I right? Abi Ebong, correct me, please. Oh.
Yes, sir. It's
You
taking
are
minutes.
raising now. Okay.
Yes, sir. So please, sir, just take it easy a bit. It's like you're too fast. I don't know if it's just me. Thank you, sir.
It's not only you. Hey, hey, hey. Because this part is very, very technical. So it's not only you. So I'm just a lot of things too, and um I'm trying to also should I say inject so it's not only you. So I second that.
Okay, I'm going to take it slowly. It's just we have a lot to cover tonight, and then what I'm taking tonight is advanced class also, but I don't want to call it advanced so that I will not scare you. But it's something that you need to know as a data analyst and then as a researcher. So I'm going to take it slowly now. Now, the metrics. or the model evaluation is very, very important. For every model that you build, you have to evaluate it. If you don't evaluate it, you cannot deploy
Sorry,
it.
sorry, sir. Sorry to
Okay,
cut it. Please,
okay.
although you've been giving real life examples to explain them, to explain, to give explanation, but please, if you can give more real life examples, I believe it will allow us to really understand better. Of course, you've been doing that, but please, if because this part is technical, it's kind of like there is advanced, so it's really help us to, you're already a guru in it, so you know everything. You might not, but we are still coming. So please, more real life examples will help us understand.
Okay, thank you so much. I will try. I will try. I will try. I will try. So that is for the regression. I've explained the regression. We have the dependent variable, and then we have the independent variable for the what for the regression. So when your independent variable is more than two or more, that means that we have what we call the multiple linear regression. But if your independent variable rather is one, that means that you have what we call a simple linear regression. So, and then we've talked about the metrics. Well, you've talked about the metrics, and then the what's it called? The model evaluation, which we are still checking. Let me quickly read this question from one of my prof. Let me quickly read it out. Okay. Uh when do we use R square and when do we use adjusted R square? Please let me take the part of R square and adjusted R square again. Now, anytime you run your analysis for regression, it's going to produce two R square. Number one is the R square, and the other one is adjusted R square. Now, the R square is like a crude oil that still have some, is it volatile? I want to remember the language that they normally use in chemistry to call all those things, all those material that they don't want in it. If I remember, I will mention it. So that means that your R square is still, there are still some errors, there are still some noise that is still inside your R square. So you using your R square to explain or to make a generalization may not be too good because of the presence of noise. Noise means error. But after we have adjusted R square will have removed those noises that you have from your what from your model. So that means that you are going to have the adjusted R square. Please note this: adjusted the R square is always greater than the adjusted R square. So anytime you are seeing the adjusted R square, you interpret the adjusted R square. Although you may leave the R square, yes, let people see the R square. Without the R square, there won't be adjusted R square, but you have to interpret the adjusted R square. So by interpreting the adjusted R square, I can now use that your model that, oh, since the adjusted R square of this particular model is 90%, I can use this model to predict. So the prediction, any prediction I'm getting from this model is going to be that at least 90% correct. So that is all about the what, both the adjusted R square and then the what, and then the R square. So we are going to bring out the two, but we are going to interpret the adjusted R square. Okay, so let's continue. So we've talked about the adjusted R square, then the mean square error. Error simply means that the difference between your observation and then the predicted value. Now that you've developed your model, you use your model to predict. What is the prediction? Let's say, for instance, now your observation value is 55 that you know, but you did not tell your model that is 55. You now use your model to predict. So by the time you now predict with you now predict the value of that prediction with the observation. When you do the subtraction, what you have there is what we call the error. It's either we have the minus or we have positive. So if the prediction is higher than your observation, so that means that we're going to have the minus. So by the time you now, that one is what we call the error. So by the time you square it, that's what we call the squared error. Square raised to power 2. So that's what we call the square error. Then when you now find the mean simply means the average. Find the average of the square errors that you have. That's what we call the mean square error. So the lower the mean square error, the better the model. Okay. Another one is what we call the root square error. Root square error. Now you've gotten your mean square error. Just take the square root. You are going to have the what we call the root square error. Another one is what we call the mean absolute error. Absolute means that we normally use absolute to correct any negative to be positive. So if you are putting any negative value in the absolute, so that value will turn to positive. That value will turn to positive. Now, that is how you to measure your what? The performance of your model. Now, the Akaike information criteria or Bayesian information criteria, that two metrics, they normally use it when you are comparing models. When you are comparing models, maybe you have developed a model for tuberculosis in Nigeria. Another person have developed a model for tuberculosis in Ghana. Another person have developed a model for tuberculosis in Niger. Now you want to compare to know the model that perform best, that capture the incident of tuberculosis. We normally use Akaike information criteria or the Bayesian information criteria. So how do we use them? The value of Akaike information criteria, the one with the highest value of the Akaike information criteria or the one with the highest value of Bayesian information criteria perform best. It performed best. There is this particular work that my HOD gave me to check for him. Then I ran the analysis. Then I plotted the what's it called, the graph. For me, looking at that graph, I can just conclude that this particular model A will perform better than model B. But thank God for another test. So immediately I just put it to model evaluation and I checked the Akaike and then the Bayesian information criteria, and I discovered that the model B that I was thinking that it will not perform better than model A performed better. So that is why sometimes you have to use this matrix that you can use number from the number that you can know, okay, this model perform better, this one is okay, this one is good. So when you are comparing 2 or 3 models, we normally use this criteria called Akaike information criteria or the Bayesian information criteria. Now, for classification, in this one that I want to take tonight, is going to be one of the things that we're going to be taking in our machine learning next month. Now, for classification, in terms of classification, we want to classify whether the outcome of this test is going to be positive or negative. Maybe someone that went for, okay, let's say HIV, is that positive or negative, or tuberculosis or diabetes or some other diseases like that, or the exam for those people in education. Okay, somebody that is writing this exam, what's probability that, okay, you want to classify it to pass or fail and some other things like that. So under the machine learning, we have what we call the classification and prediction. So under the classification, how do you measure the model that you are using for classification, any classification model? How do we measure that? For classification model, we have the accuracy. We have the accuracy. There is a formula that we normally use to do the accuracy, but your system can can produce the accuracy for you. So you are going to know the accuracy of your model, how well your model is being accurate. Let me just put it like that. So proportion of correctly classified observation. So if you are giving your model, let's say for instance, you've on your own, you know the result already that, okay, this person has tested to COVID-19, tested positive to COVID-19. Now you have developed a model that you can use to classify whether somebody is positive to COVID-19 or not. Now you know that this particular person is positive already. Now putting that all the factors, all the variables that you measure to classify that on your own, that you know that this person has developed the COVID-19 symptom. If you now put it in your model, if your model can also classify that person that has discovered it as well as that person has a COVID-19, so that means that the accuracy of that your model is high. So that means that it is what's it called, correctly classification. That is true positive. True positive, although that person tested that person is positive to COVID-19, and when you now use your model to classify it, your model also supported that is tested positive to COVID-19. That's what we mean by the accuracy. So precision, proportion of true positive out of all the positive predictor. We have true positives and then we now have what we call the positive. There is I think is a golden. I want to remember that particular test. That's, you know, someone may tested positive to HIV. That is why they normally say, okay, one test. You cannot use a test to judge. That's why they will tell you that anybody that want to carry out any test, they will ask you to test it like 2 or 3 times so that they can really know. They can really know. Okay, let's say for instance that they've used one machine to test, and then the machine is telling you that it is 70%. Another machine is telling you that it is 80%. Another machine is telling you that it is 90%. How do you know the one that is correct? That is the essence of what we call the positive, what's it called? The positive outcome. So from all the positive that you have, although we have all the positive, the first one is 75, the next one is 80, and then the next one is 90. So how do we get? That's what we call the precision. Then another metric is what we call the recall. Recall is one of the metrics that we normally use to evaluate a classification model, whether it is sensitivity or true positive rate. Another name for sensitivity is true positive rate. What did I mean by that? That means that your model correctly classify that this person is positive to this particular disease. This person is negative to this particular disease. This person will pass this particular exam based on the factor that you supply. This person will fail this particular exam based on the factor that you supply. This machine will work very well based on the factor that you supply. This machine will not work very well based on the factor that you supply. This particular plant will grow very well based on the factor that you supply. This particular plant will not go very well based on this factor that you supply. Another one is what we call the specificity, proportion of actual negative correctly identified. If your model can correctly identify the negative, oh, this person tested negative, when they put it in your model that you've developed, your model also verify that this person tested negative. So that is what we call the specificity. Then we have the F1 score. That's another method to do or to evaluate our model. Then we have area under the curve. So area under the receiver under curve. Okay, area under the receiver under curve, ROC. That's how we normally put it. So it measures the trade-off between the sensitivity and specificity. So by the time we're going to perform all this now, when we get to our practical, there's another one what we call the confusion matrix. Confusion matrix. So confusion matrix will tell you, okay, the table will show true positive. Those categories that your model was able to categorize that this is positive, and in true sense it is positive. Then we have true negative, and in real sense it's true negative. Then we have false positive. That thing is negative, maybe because of your error, maybe because of the error in your model. The model predicted that it is positive, whereas that thing is negative. It is called false positive. And then we have the false negative. That person is tested positive, but your model is saying that it is negative. That is what we call the false negative. So you can see that when you plot what we call the confusion matrix. So we're going to see that tonight. How do we evaluate the time series model? You know, we've talked about the regression model. We've talked about the classification model. Now we want to talk about the time series. How do you evaluate the time series model? Number one is that we normally use mean absolute percentage error. Mean absolute percentage error. So that means that you will first of all find the error. Once you find the error, you find the absolute. Then you find the mean before you now find the percentage. Did you get it? You find the error. You know how to get the error. The difference between your what's it called? It's measured the percentage error between observation and prediction. So the difference between your observation and the predicted value, that will give you the error. So by the time you take the absolute value, anytime you are taking the absolute value of negative, is going to give you positive. So by the time you take the absolute value, you are going to have what we call the absolute, absolute error. So by the time you do that, then you cannot find the mean. So by adding all those values that you have divided by the number of observations, so you are going to get the mean, and then you are going to find the percentage. All these things I'm mentioning, once you run it in your system, in your your statistical software, is going to produce all this. So another one is mean square prediction error. Square error between the actual and predicted value for future prediction. Another one is what we call the autocorrelation of residual. Now, there is what's it called? There is a test that is very, very important when you are dealing with your what's it called, whether it is regression, whether it is classification, whether any form of data, you have to check what we call the autocorrelation. They normally use autocorrelation in time series, but in regression and some other thing, we call it multicollinearity. Multicollinearity. What do they mean by multicollinearity? They want to check whether a variable, two or more variable in your model does not say the same thing. Let's say, for instance, now I have variable A that is talking about the age, and another variable B is still talking, is saying something relating to age also. That means that there will be a presence of autocorrelation, and that one will really affect your model. So that means you have to check for what we call the multicollinearity in some linear regression, or in some other what, in some other models. But in time series, it is called autocorrelation. Ensure no parts remain in residual. Tested using the Durbin-Watson test. So the Durbin-Watson test is a test that we normally use in time series to do what? To do autocorrelation. Durbin-Watson test. We normally use it in time series to do autocorrelation. Then we have what we call the cross-validation. The cross-validation is also one of the metrics that we use in machine learning. So the predicting under the machine learning, I told us that we have the classification and prediction. So the predicting part of machine learning, we also have what we call the time series there. So we normally use what we call the cross-validation. Split the time series into training and testing period. I told us that in machine learning, we normally divide data 70-30. Some can use 80-20. You will use 80 to train your model. You will use 20 to test it. You can use 70 to train your model, and you can use what's it called? You can use 20 to you can use 30 to what, to test it. Split your time series into training and test period to evaluate forecasting accuracy. So by the time you do that and you test your model with the remaining data, you can now conclude that okay, this model is now good for prediction. Now let us move to the time series analysis. Time series analysis. What is time series analysis? Time series analysis involves analyzing data that is collected sequentially over time. Over time. Anytime you are using a data, whether it is monthly data or weekly data or yearly data or quarterly data, and you want to perform analysis on it, we normally use what we call, when you are considering time, please note that when you are considering it over the time, we normally perform what we call a time series analysis. Time series data typically have a temporal order, and the goal is to what, to uncover patterns. So the goal of the time series is to what, is to check the pattern. Let's say over the 10 years now, let me check the performance of my students. The students that have been taking for over 10 years based on the exams. Let me check their performance. I will check, okay, this particular year, let's say 2010, there is upward in performance. What really happened? What are the factors that happened there that caused the upward in that? There is this also year, there is downward. Like a particular analysis that I just did for one of my clients is on something like relating to death of the, what's it called, all these small baby, let's say mortality. So now she collected the data, I think over 10 years. So by the time we do the time plot, we discover that, okay, in 2020, there is downward decrease in mortality rate. What really happened? So by the time we started considering those factors that surrounded 2020, we discovered that it's a COVID year, and there are a lot of equipment that each state they bought in order to tackle those COVID. So by the time they are doing those things, the rate of mortality decreases. And then we still discover that around 2022 to 2023, there is an upward in the trend of mortality rate. So those are the things that the time series will tell you, and then we check some factors. By the time, let's say for instance, now, if I want to make for a suggestion based on that research, I can say that to those of the machine that they used in 2020, can we adopt that? By the time we adopt that, let us see it over the 5 or 6 years and see whether the rate of mortality will decrease, because we can see his work in 2020 that the rate of mortality decreases. So that is how we normally check. We check the trend, we check the pattern, then we check the seasonality. This thing that is occurring, is this seasonal? Is it every season? Like the times of rain. If I want to model a model, if I want to develop a model for rain, I want to forecast the rain. So that means that it's going to be a seasonal data, because rain is season. It's not everyday things. So that the data that I'm going to collect is going to be, if I want to collect the rainfall data is going to be a seasonal what? A seasonal data. So now the key feature of time series data, please and please, if I thought you don't get anything in this training so far, which is not true, time series is very, very important. We have few people that can handle time series data, but if you can handle time series data, is a money for you. Is a money. This project that I'm telling you about, they've given it for one analyst. That person cannot do it. So immediately they just came to me. I just told them my price. So, and I told them that I told the woman that I'm going to deliver, and I gave them the hour. Okay, give me 2-3 days. I'm going to do it. It's a purely time series. So immediately I saw it, I know that it's not everybody that know how to do the time series. And this is the amount. So the woman just said, can you do it? I can do it. And she paid. So time series is not just ordinary data, ordinary analysis that you will see row size analysis using R to run, using SPSS to run and bring out the result. No, they don't know how to do it. So if you know how to do time series data, time series analysis is a let me just say is plus for you, like 6++. So please and please, if you don't get anything, you can go over the video again, or you send me a DM. We are still going to do the practical part of it tonight. Okay. Now, what did they mean by temporal dependent? What happened yesterday will give room for today. Let me put it like that. The data of the past we normally use for the future. So time series data will start from the back going forward. Let's say, for instance, now like the one that I mentioned, they started from 2019. So from 2019, what happened? We moved to 2020, we moved to 2021, we moved to 2023. So the moving of the time series data depend on the past data. So that is when you use the word lag. The word lag is the statistician language. Assuming I'm presenting this to only statistician, I will not be using previous. I will not be using back. I'll just be telling them that for the next data, it depends on the lag of the second data. So if I mention lag, that means that I'm referring to the back, but it's a language in statistics. So, but I will not be saying that because it's returned to jargons, but I'm using lag. So now, time series data depend on the previous one. So observation are not independent. Current value depend on the past value. I've mentioned it. There is nothing like independent. The only independence in time series is the time. Time is independent. So everybody depends on time. So in time series, so we normally use what? Observation, your data that you have are not independent. Current value often depend on the past value. So it lag on the past value. Another thing, another key feature of the time series is the trend. If you are doing a work of time series for your client and you don't show them the trend, the work is half big. You have to let them see the data that they have. You have to let them see the behavior of their data. By the time you visualize it, they will see, they can bring out useful information from the visualization. That is what we call the trend. Then we have the seasonality. We are going to check the regular or predictable fluctuation. You want to check, is it this fluctuation that we are seeing? Is it daily fluctuation? Is it monthly? Is it yearly? So let's say, for instance, now for the female that they normally do the period, so that one is monthly. So if you want to track, let's say, for instance, now they have problem with the period, they can track it over the year or over 2 years. They can track it, and then from there you can check whether the pattern is regular or what, or irregular. So in that sense, it is what we call the monthly data set. So in that sense, it is called the monthly, which is under the category of what, of seasonal. So we have what we call the cycling pattern, fluctuation over irregular interval that you cannot even predict. It goes up today, like what's it called? Like the world of crypto, the world of cryptocurrency. So it goes up today, it's come down tomorrow. We want to model that. There is what we call the cycling pattern, fluctuation over irregular interval that are not tied to a specific frequency. You can't even say that it's moving like this, it's moving like this, moving like this. In this particular sense, under the machine learning, we categorize them as unsupervised learning. Unsupervised learning. So the model that you are going to develop for them is the model of unsupervised. You don't need to supervise that model. The model will catch up with the pattern or catch up with the movement by its own. It will decide it. Then another thing is what we call the noise. Noise, a random variation or irregularity in the data set. Noise is used in time series, but in regression and some other model we call it error. Now, the goal of the time series analysis, what do we want to achieve while performing time series? Number one, you will understand the pattern, the trend, and variability. That is the first thing. That description. We are going to know the pattern at which they are moving. You are going to know the pattern. Then from there, you can see, the way this thing is moving is going to get worse with the data I'm seeing. So from there, you can speak from the data. So it's going to show you the pattern, the trend, and then the variability. Another one is the forecasting. Predict future value based on the past observation. We normally use it to what? To predict. Let's say, for instance, now, we want to we have a school. Let's say we have a school that we have 20 students, and over the time you discover that every day they are bringing 2 students, 1 student, 3 students, 4 students. At the end of the month, you have a data for the number of students. Now let us now say that you are the one that is futuristic, that in the next 2 months, or in the next 5 years or 2 years, this place that I'm using, it may no longer contain people again. How many students I'm going to have by that 2 years or 1 year based on the data that I'm seeing now? So by the time you now collate all those data that you've recorded, your present data now, and then the past one, by the time you collate it together, you check the trend, you check the pattern, then you can now develop a model that can predict. So by the time you now develop model, you can predict that, okay, let's say in 2 months, I realize 20 students. Okay, now, how many in 2 years? That would be how many months? That would be 24 months. You will put 24 months in your model. Your model will predict the number of students that you will have in the next 2 years, so that you will start working towards that. It will not be that next 2 years that you start thinking that we're supposed to go and buy land to build another building. We're supposed to get more chair. No. By that time, it will not meet up again. That is why every country that wants to develop must make use of data to predict ahead. That is why you will see a lot of grants in diseases. You can discover, okay, this particular disease in the next 20 years can do this. You can develop a model. Okay, that is essence of the model that we normally develop, so that the future occurrences, you can know it, we can prepare for it. It will not be like what's it called? Something that you don't prepare for. It will not be like something that you don't prepare for. So that is why we normally develop model for what? For prediction and forecasting. Then modeling, build model to capture relationship in data. Now, as far as this class is concerned, we are not going to build any model here. I'm not going to teach you how to build a model. Yes, it's only those people that will come for the advanced class that we're starting next month that we're going to be checking how to build a model. In that class, I'm not going to be telling you that how to read your data inside. You know how to read your data inside R. You know some things in R. So I believe that you'll have acquired a foundational knowledge from this class. Now, the existing model are this that I mentioned. The AR that you are seeing here is one of the model in time series. It is called auto regression or auto-regressive. Let me put it like that. Auto-regressive, AR. The ARMA that you are seeing here, ARMA, is called auto-regressive moving average. ARMA is auto-regressive moving average. Those are the models in time series that we normally use. Then we have what we call the ARIMA. ARIMA is auto-regressive integrated moving average. ARIMA is auto-regressive integrated moving average. Then we have what we call the SAMA. SAMA means season, season auto-regressive moving average. So when you have a seasonal data, so you cannot use ARMA or use ARIMA, but you are going to use what we call the SAMA. Then we have another one called SARIMA. We have another one called what? We have another one called SARIMA. What is SARIMA? SARIMA simply means that what's it called? Season auto-regressive integrated moving average. Those are the models that we normally use in time series. So it depends on the data that you are working with. The data that you are working with will determine the type of model that you have to use. And if the data that you are working with does not support any of this model, that means that you have to develop a model. And then the cost of you developing a model, you are it is money. You are launching yourself to what? To money. Ability to develop, to know how to develop model yourself. It is what? It is money. Now, control, adjust or optimize process based on the observe behavior. So, like I mentioned the other time, if you are building a model, you put the first variable, you discover that the R square increases, you put another variable, you put another variable, immediately you put variable, and you discover that the R square, the metrics that you are using is decreasing. So that means that you just have to stop at that point. So that is how we normally do in both time series and then in the regression. Now, this is the steps. Let's say at the end of this class, someone now call you, or you saw an advert or a project that can you handle time series. Don't get scared with the formula. Don't get scared with how do I start. These 5 steps that you are seeing here, once you follow these 5 steps, you'll be able to do your time series analysis successfully. Number 1 is visualization the data. Visualizing the data rather. So that means that you have to first of all plot the data. Once you plot that data, you are going to check the trend. You are going to see the pattern. You are going to see the, what's it called, whether it is increasing or decreasing. So we use what we call visualizing the data. Use line plot to observe the trend and seasonality. That's number 1. It's more or less like that's its own descriptive. So that's number 1. Then number 2 is decomposing the time series. Decomposing the time series. So what did I mean by decomposing the time series? It means that you are going to what did they mean by the decomposition? It means that you should be able to decompose your data, split your data, and be able to bring out the trend from the data. Let me check the trend from the data. Then seasonal, you have to check the irregular pattern over time. Then the residual, the noise or error component. So these 3 things, you have to get it when you are decomposing your data. Remember, the first thing is you are going to visualize your data. By the time you do the visualization, these 3 are combined together. But the next step is you are going to remove them one by one so that you can interpret them one by one. So that's what we call the decomposition. Now, you are going to check whether you check for stationarity. Remember that yesterday I taught us what's it called, the normality test. In time series, we normally call this test a stationarity test. You want to check whether your data is stationary or not. So when your data is stationary, that means that your data is normal. When your data is not stationary, that means that your data is not normal. So unlike the yesterday that we used Shapiro-Wilk test, for time series, we normally use what we call the Dickey-Fuller test. Dickey-Fuller test. Now, Dickey-Fuller test is more or less like the R square, which is crude. Now, the one that is more or less like adjusted R square here is what we call the augmented Dickey-Fuller test. Augmented Dickey-Fuller test. 2 people come together, the Dickey and the Fuller. So the joint name is what we call the Dickey-Fuller. So the augmented Dickey-Fuller test is a test in time series that we normally use to check the stationarity or to check the normality of a particular data. But in time series time, we don't use normality. We use what? Stationarity. If I say your data is not stationary, so that means that your data is not normal. So we normally use augmented Dickey-Fuller test. So after you visualize your data, you've decomposed your data, then you check for the stationarity by using what we call augmented Dickey-Fuller test. Now, after that, you are going to differentiate. What did they mean by difference? Immediately, your data is not normal. It is not stationary. It is non-stationary. So use difference. Difference is just our knowledge of, I don't know, maybe we know the, what's it called? The calculus. Yes, our little calculus in further maths. So that's what we call the difference. Difference just means the backward difference. We have the forward difference and some other difference. So you difference it. All this that I'm saying is not you that you'll be using your hand to do it. You can use it in your, just use any of your software to do that. Then after you've difference it, immediately you difference your data, that data will be stationary. So by the time you do the differencing, you can also check the you can also check the stationarity again by using augmented Dickey-Fuller test. So by the time you've done that, then the last one is to forecast. Use a model or build the new model or build the new one for forecasting. So after that, then you can now you cannot forecast. So that means that you've come to the end of the of the time series by developing the model or by using the existing one to forecast. So these 5 steps are very, very important in time series. Now, advanced topic in time series. This one is advanced topic in time series for those people that will be doing your PhD, or for those people that will be getting grants for research. So we have what we call the stationarity and differencing. If the data is non-stationary, how do we do it? Is that we use the transform like log or differencing, and then we have some other method that we can use in doing that to make our data stationary. Another one is what we call the multivariate time series. From the one multiple. So when you have more than one variables in time series, how do you handle that? We normally use what we call vector auto regression for multiple relating time series. So that is what we normally use. VAR, not the one that we normally use in football. So this one is vector autoregression for multiple related time series. Anomaly detection. If you want to identify anomaly in time series, then deep learning
Your line is breaking, sir. Your line is breaking.
is a method. Is under unsupervised learning. Yes, under machine learning. So our starting our next class month. So that's what we'll be as the as so this is the flyer. If you have anybody that wants to join February 4, starting February 4, and it's going to run for going to be meeting 3 times per times that we have 12 to do, and the price is just 30,000. So we're running this. Can you hear me now? Okay. Can you hear me, please? Sorry, the network logged me out. Can you hear me, please?
Yeah, it is better
Yes,
now,
sir,
sir.
we can hear you. It's better now.
Okay, thank you so much. So where did you stop? So can you see my screen now? Can you hear me?
Yes, we can hear you now.
Okay, good. Okay, where did you stop?
You were talking about maybe the upcoming boot camp or
Okay,
so.
okay. Oh, thank you. Thank you. So those are the things that we're going to be checking in our upcoming bootcamp. So please, if you have anyone that wants to join us, you can help us tell them that we're having this, or you want to expand your knowledge in R. So the only software that I'm going to be using there is the R software. So, and then let me say this tonight. You've built your portfolio, everything that you've learned in this bootcamp. Please put it in your CV. And then if you see any work relating to data, collect the work and lay your hand on it and start doing it. So if you encounter any problem, you still have a room to go and watch that video for a year. Go and check it. Then after you've watched the video and you still don't understand, you can contact me and I will see what I can do to that. So please, and then put it in your CV. You have a knowledge of R, you have a knowledge of SPSS, you have a knowledge of the Excel, you have a knowledge of Stata. So please, you have to develop that courage. And then the batch B of this camp is coming next March, so that you can help us tell your friends or your colleagues that they may have interest in this. Maybe they want to see, okay, what is the outcome of the first one that you guys have done, something like that. Please help us to tell them what you've gained in this class. So the method that we use in this class. So help us tell them that they should enroll. So the next one is the next one, which is the batch B of this one, is coming March 14. That one is going to be 6 weeks, and then it's going to be 25,000 naira. Okay, so that is all for tonight. Thank you for listening. So before we move to the practical part, I would love to welcome question. You have the floor now. Please, you can ask your question. Thank you. Okay, Mr. Laide, go ahead.
Okay, sir. You gave an example of the other time. You gave an example that a situation whereby when you pick your phone and it suggests the regularly used app, the regular used application for you. So and the way you've been talking about modeling, is it different from algorithm? No, if you say modeling and if you say algorithm, because you know, with the step by step of what you've been saying, it's kind of so what's different? Is there any difference between modeling and algorithm simply?
Oh, there is difference between modeling and algorithm. Now, algorithm simply means that the step-by-step instruction that you give to your computer, the step-by-step instruction that you give to your computer to perform, that is what we mean by the algorithm. Then algorithm makes use of what we call the flow chart. Let's say, for instance, now, if you are coming to my house, when you get to T junction, move to the left. When you move straight down to the left, you will see one yellow house. By the side of yellow house, you see another road. So those are the algorithms, step-by-step instruction. If you are not doing that for your what? For your what's it called? For your model, it is called the algorithm. Are you together? But the model is what you build based on the algorithm. Let's say, for instance, now if I want to use a regression model, I'll first of all have my x, I will have my y. What is the next thing? X multiplied by y, I will have it. What is the next thing? I will find x squared. What is the next thing? I will find y squared. So all those step by step that I'm performing, it is what we call the what? The algorithm. So algorithm is the step by step instruction given to what? Given to your system. I don't know, maybe I've answered that.
Well, I will.
It is not clear. It is
Something
not
like
clear.
yes,
Okay.
because
Well,
what you've been explaining about modeling also, it seems
okay.
familiar with because you made mention of testing modeling. If I may right, yes, time series. You made mention of time series. You made a, is it not I mean, I still want to be clear about it.
Mr. Laide, algorithm simply means that the process that you follow to actualize your model, or the process that you follow in actualizing your model. That is what they mean by the algorithm. So that's why you will see them, they will draw line, they will draw flow charts. So flow chart goes with their algorithm. That will tell you the system, the movement. Or let me put this for so that we can understand better. When you see a conceptual framework, if you see a conceptual framework drawing, so the way they move, okay, when you move from your social demographic, you move to what's it called, the factor that's affecting this, you move to this. Those things that you are seeing are just the algorithm, step by step, that they are using, that they use in actualizing their goal. So that is just the simple my own simple understanding about the algorithm. So algorithm is the step by step instruction given to your system to perform. So, or maybe better still, you can still go online and still check more. But the universal or the intersection of the definition for algorithm is that algorithm is a step by step in what, in performing a step by step instruction given to your what, given to your system carry out the instruction. So that is my little knowledge about the algorithm.
Okay, sir. Can R programming or perform that, or that is now that, or that is another thing entirely?
Why not? You can perform it. All this code that you are writing step by step, you want to plot a graph. Okay, the bar plot, then inside the bar plot, you have some variable inside. That step by step instruction that you are giving, that the your programming, your software is following, because you want to actualize just one goal, the graph. It is algorithm. Algorithm is just the language that they use, they are common use in computer science. So simple layman language is the step by step instruction. As you are writing your code, you are doing the algorithm already. You are writing those code step by step, step by step, step by step to actualize one goal. So, Mr. Ade, any other question?
Let's go ahead, sir. Let's move forward, sir.
Okay. Any other question from our dear audience? Any other question?
None
Okay.
for now.
Okay. Let's switch to our. Let's move to our practical. Let me share my screen. So tonight, let me see. I want to use R Studio tonight so that it won't look like, oh, what else why you have been using R. Let me see. I want to use R Studio. So can you see my screen? Can you see my screen?
Yes, we can.
Okay. So let me These are the work that I've done in the past. So let me remove this so that we can start. Now, open the new script. Okay, good. I have the new script. Then open. I have the code where open. Okay, advanced R and advanced analysis R. Let me open this. Okay. Now tonight, I'm going to be using two data sets to perform those analysis that we're going to be seeing tonight. Number one is our normal empty cars that we have been using, and then another one is we're going to be using the air passenger for our time series. Air passenger is one of the input data in R that they have. They collected the number of people that is entering aeroplane, the aeroplane, yes, they bought aeroplane for over some years. So they collected the data together, they put it in the R database. So we can start it from there. So let's start. So linear regression. So tonight we want to start with the linear regression. So I'm going to load the data I want to use tonight, the MCAR. Unlike our normal R that we normally use Control R, in R Studio, look at this. Can you see my console? You see run? This is the practical section. We have to be, this is interactive.
Yes, sir.
So, so this is where you will normally run it. There is no Control R here. So once I press this now, I'm going to move. Can you see this? So we have the loading data MCAR. So the data is here already. If you look at the data, this is the MCAR. Okay. Now, fit simple linear regression. I want to fit the mass per gallon, the MPG as the response. That means that the NPG is my what? Is my what's it called? My predictor. No, it's not predictor. It's my outcome. It's my dependent variable. And then the weight, W, the weight of the car is my predictor variable, which is WT is the weight. Now, how do we find a simple linear regression? Remember that under the simple linear regression, I told us that we only have one dependent variable and one independent variable. So the one dependent variable here is MPG, and then the one independent variable here is the weight of the what? Of the car. So if I want to find the simple linear regression, we have the model for simple, then LM. LM is the what? Is the what's it called? Is the code or the function in R that we normally use to perform our what? Linear regression. It is called linear model, LM. So by the time you put the LM here, then the variable that you want to your dependent variable will come first, which is the MPG. Then this symbol is called sim. How do we get it? Your escape button. Once you get your escape button, the button below your escape button, just press shift that. Let me show you your escape button on your system. Once you press that shift, there is a button below it. You will see shift S, shift that button. So it's going to give you that symbol. It is called sim. 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 So that is how you are going to get that. So by the time you do that, then the data that you want to use for this, it is empty car. So by the time you do that, you are going to have the model. Control R. Oh, sorry. I said Control R. You are going to run it here. Once you run the model, okay. Then let us do the model summary. By the time we do the model summary, we're going to see some features there. Control R. Now, can you all see this? Can you see this, please?
Yes, sir.
Where,
Yes,
okay.
sir.
Now, if you look at this is the result of that linear, simple linear regression. So if you look at this, we have the estimate, the intercept is this, and then we have the weight. The value for the weight under the estimate is minus 5.344. Then we have the standard error, we have the t value, and then we have the p value. Now, if you look at it further, we have the multiple, we have the r square. Our r square is 0.7528. This is 75%. And then we have our adjusted r square. Our adjusted r square is 0.74446, which is 74.46%. Now, if you look at this now, what this one is telling us that by the time you write out this model, let us write out this model now. This model is going to be y is equals to, then the intercept, the coefficient of the intercept is, we have 37.2851. Then we're supposed to have plus weight, but since we have the negative here, it's going to be minus times plus is going to be minus. So we're going to have minus 5.3445. Then you have your x, which is your weight. So that one that you just put down, let me take it again so that you can write this down. Is going to be your y. Your y is your dependent variable, which is equals to, in this case, our y is mgp, which is equals to the intercept of that model is 37.2851. Then we're supposed to have plus, but because of the negative that we're having here for the weight of that car, so we're going to have minus 5.3445. Then the weight WT. So that is the model. Now, what is that one is telling us is that if you give me any weight of what of the car, I'm going to predict the MGP for you. Let's say, for instance, that if the weight of that car is what is 10, by the time you multiply that 10 with the coefficient of this, then you add it to this, you are going to have the MGP. What is the interpretation of this? Let me take it slowly now. What is the interpretation of this? You have your y is equals to 37.2851 minus 5.3445 WT. What is the interpretation? This one is simply telling us that a unit increase in weight, will lead to minus 5.344 decrease in MPG, provided that all other variables remain constant. Let me take it again, the interpretation. The interpretation simply means that a unit increase in weight of that car will lead to minus, what's it called, minus 3.445 of MPG, provided that all other variables remain constant. Another interpretation is still this. A unit increase in the weight will lead to 5.344 decrease. And by the time I mentioned 5 point, I didn't put minus and put decrease. No. If you are not using minus to interpret it, you are going to use the word decrease. If you are using minus to interpret it, you are not going to use decrease. So that means that a unit increase in weight of that car will lead to 5.344 decrease in the MPG, provided that all other variables remain constant. Okay, let's move to the overall perform model. We have the R square, then we have the adjusted of this adjusted R square. Can anybody interpret it for us based on the knowledge that we've acquired? What is the interpretation of this adjusted R square? Mr. Lide, are you still there? Ibukun, are you there? Hello, can you hear me, please?
We can hear you, sir.
Okay. What is the interpretation for this R square, adjusted R square? What is the interpretation for this adjusted R square, please? Anybody?
Okay, adjusted R square is the one that has already been seasoned already, like the one it has already been refined. So that's
Yes.
what it means. The R
What is
square has been taken.
what is the interpretation?
Yes, sir. I think for my own little knowledge, the interpretation is the model can only reckon with, I mean, can only say 70%. I mean, the whatever happened was just like 70%. The other 30% is an influence of an external variable.
Okay. Well done. You tried. Any other
Okay,
interpretation
sir. I
based on
have.
what you had?
Yes,
What
sir.
do you like?
It means that the model is. It means that the model is better, being that the adjusted R is lesser than the R square.
Okay. Any other interpretation? Because if you are working for a client or you are doing research, you have to interpret everything that you have there. Because in the course of the interpretation that we can use it for innovation. So any other answer, please? Okay, let me quickly explain this. The adjusted R square that we have there is 74.46. It simply means that out of the total variability that we have in our MPG, the weight of that car can only account for 74%, where the remaining percentage is due to other factor that is not in this model. Let me take it again. Out of total variability that we have in our MGP, the weight can only account for what? 74.46. Then all other one, the remaining percentage, can be accounted for the other variables that is not included in this our model. So that is how we interpret that. So let us see, let us plot the data and let us see the relationship. Can you see this graph? Can you see this graph here? Simple linear
Yes,
regression.
sir. Yes,
Okay.
sir.
Now, by the time you plot this, without me looking at your model, I should be able to say the relationship between this and this. What is the relationship? What is the relationship? Now, look at your coefficient. The coefficient that we have here is minus 5.344. So because we are having a minus here, that means that the relationship between the MPG, the miles per gallon, and then the weight is negative. So that means that as the weight increases, then the miles per gallon decreases. So the relationship between the two are negative, even from the graph, because all those points is looking at the concentrated more from your right hand side upward, not from the left upward. So if it is from the left upward, so that means that it is a positive relationship. So we checked that yesterday when we were doing our scatter plot for correlation. So I don't know, maybe we understand that, please. What message do we have here? Okay, the relationship is inverse. Okay. So that means that as one increases, the other one decreases. So that is inverse relationship. Okay, good. So this is just another way to bring out our graph. So let's move to multiple linear regression. Now, fit a multiple linear regression model, the MGP, then we want to check the weight and then the horsepower, HP. We want to check the weight and then the horsepower. You know, the first one is only the weight that we checked. So, but now we want to check the weight and the horsepower. But before that, let me put the line so that we can see. Let me put the line. Okay, good. Look at this line now. Look at this line. So this line here showing us that there is a negative relationship. because the line is starting from our right hand side. Although, look at it, this is 5. Then we have, so what's it called? This one is higher than 5. That's why we are seeing 5.344344. So this is the starting point, 5.344. But the starting point here, the relationship is negative, is inverse. So that is why they are having the minus. So this is the 5.344, which is the coefficient that we have here. The coefficient that we are having here. So now let's move to the multiple now. The control R. Run. So now let's check the model summary. So this one is just this. Okay. Now, if you look at this, this is the intercept. This is the weight of the car. This is the HP, which is the horsepower of that car. Now, the estimation, this is the coefficient that we have. There is still a what? The coefficient of weight now is what? Minus 3.877, which is also the relationship is negative. They have a negative relationship. The same thing with the horsepower. There is a negative relationship. Now, let us come to the adjusted R square. Look at the adjusted R square. Can you see now that it has increased? Remember that when you have just single one the other time, the adjusted R square was 74.46. But now we've added the horsepower, another variable called horsepower, and then the adjusted R square has increases. Can you see now? Anybody can you interpret this for me, please? What is the interpretation of this? I just want us to get how to interpret. The interpretation is very, very important. Can you interpret this, please? Anybody?
So which one?
This one that you are seeing for the multiple linear regression. The adjusted R square is 0.8143. What is the interpretation?
Okay, let me try.
Please go ahead.
Okay, out of the total variability, the weight accounts for 81.48%, and then the remaining variables like the horsepower account for the remaining percent.
Okay. You try. Any other interpretation before I give my comment?
Yes, sir.
Please go ahead.
The model can only account for 81.46%, if I'm right, of the weight, while the other many variable is the result of an external factor.
Okay. Any other interpretation again? Ibukun, are you there?
Yes, sir. But my network has been very bad.
Oh, okay. Sorry about that. Okay, let me quickly explain this again. Our first speaker, you tried. The second speaker, you tried. But our first speaker, it is only the weight that you consider, because but in this our next one here, which is the multiple, is not only the weight. We have horsepower, which is HP. So in interpreting this now, this is just what we have. What out of total variability in the MGP, weight and horsepower, not only weight and horsepower can only account for 81.48%. Weight and horsepower can only account for what? 81.48%. Then the remaining variable can be accounted for what? For the remaining percentage can be accounted for with other variable that is not included in this model. Other variable that is not included in this one, which is 80.4. Okay, someone said, okay, the weight accounted for 81.46 variability. The rest is this accounted for that factor. Yes, you are right, ma. You are right. You are right. So that is the interpretation for that. And then if you now see that the adjusted R square has increases, so that means that this the horsepower also contributes to the outcome. So that means that the first one that we used the ordinary weight, we have 71 or 74. Then immediately we added horsepower, we have what? We have ordinary what's it called? Also, we have 81.48. So in your own time, okay, maybe at your own leisure time, if you want to practice it, you can pick another one, pick horsepower and find the find the simple linear regression for it and see what you are going to have. Now, this one is what we call the diagnostic plot to check assumption. There are some assumptions that we normally use in statistics. Every model in statistics follow assumption. I think I've explained. I explained the quarter by quarter plot, the QQ plot yesterday. Then we have the residual versus fit. We have the scale location. Then we have the residual leverage. So all these are the model checking. We normally use it to check our model. If you look at this line under the QQ plot, you will see that most of our observation, they have more concentration on this line. So that means that there is a strong relationship here. So the model check, if you are checking the model here, there is a what? There is a strong. Then the model versus residual. Look at this fit. Residual versus fit. If you look at this, the what's it called? The residual is coming from the positive. If you look at this broken line, we're having 0 here. So by the time the residual is coming, it's got to a point that it went straight to negative and still pick up again. So this one is showing us the residual, the error versus fit. So that means that the relationship between the error and the fit model that we have, the relationship that is occurred between them is not the one that is we can't say it is upward relationship or downward relationship. So it's a mix. There is a downward relationship and also picked up again. So this is some graph that we normally use to check the behavior of our model. It is called a model diagnostics. It is called a model diagnostics. So we are still going to how would I put it? There are some statistical times that I don't want to be using here because of some participants that we have. So in nutshell, we normally use model diagnostics to check our model. So let's check the logistic regression. Logistic regression, that's the next one. So in this logistic regression, remember that in logistic regression, your dependent variable must be dichotomous, must be 2, yes or no. Now, if we look at the one that we want to use for logistic here, the one that I want to use for the logistic here, the automatic and the manual, the car that are automatic and the car that is manual. So it's either your car is automatic or your car is manual. So that means we have 2 outcomes. So for the automatic will take 0. That's the meaning of this. The automatic will take 0 and then the manual will take 1. So immediately I finish this class, let me share the code straight so that it will not be like the one of that yesterday. So the automatic is 0 and then the manual is 1. So and then the manual is 1. So by doing that, we have our 2 outcomes, which is what? Which is automatic and manual. So let me run this control. Now I want to fit the model. Remember that when we wanted to fit our model for simple linear regression, we use LM. LM simply means linear model. But in the case of logistic regression, we normally use what we call GLM. GLM simply means generalized linear model. It's a family of logistic, it's a family of the Poisson, they have many families there. So it is called the generalized linear model. So GLM, then the GLM is equals to we have the automatic sim. I want to check the horsepower. I want to check the weight. Then the data is the empty cars. Then what is the family? I told us that in that family, we have different children there. So the children that you want to use, what family? It belongs to the family of binomial. Bi means two. So anytime you are using the logistic regression belongs to the family of binomial because the outcome is just two. And then the binomial has two outcomes. Is either success or failure. So the family that is belong to is the family of binomial. So by the time you do the what's it called? You run it now, Control R. So after running it, then let us do the summary of the model. Now we have the summary of the model here. We have the summary of the model here. If you look at the summary of the model, there is a positive relationship between the horsepower and then the outcome. Then there is a negative relationship between the weight and then the outcome. Now, if you look at this, I didn't mention this the other time. Is the relationship significant or not? If you look at this, we have 0. On this one is the p-value. So if you look at this, we have 0.04091. So I told us yesterday that anytime you are seeing 1 star means that it is significant. Anytime you are seeing 2 stars, that means that it is moderate significant. But anytime you are seeing 3 stars, that means that it is highly significant. Highly significant. So the significance of these two relationship is their significance. So they are what? They are important. Then in logistics, we normally consider what we call the odd ratio. The odd ratio. The odd ratio simply means the exponential of your coefficient. But we can also calculate the odd ratio. That is what I have here. Calculate the odd ratio, the exponential of this. So if you take the exponential of your coefficient, you are going to get what we call the odd ratio. So we use the odd ratio to also interpret. Then in logistic regression, we have the AIC. We have the AIC. This is the Akaike information criteria. Let's say I have another model let's say I have another data too that I use to model, or I have another model, and or this particular logistic regression, they also use it to perform another analysis that related to this one that I was doing, that's related to car, and they now want to see which one they should take between my model and the other model. So by the time they check the AIC value here, our AIC value here is 16.059. If they check other AIC value and they discover that the AIC value is around 15 point something, so that means that the one with the highest the AIC, Akaike information criteria, or the Bayesian information criteria is the one that is okay for the prediction. Let me put it like that. So let me check the odd ratio. Okay. So where's the odd ratio here? Okay, yes. The odd ratio, the value is here. This is the odd ratio here. So for the first one, our odd ratio here is 1.56 times 10 raised to power 8. That is the first odd ratio. So the second odd ratio here, we have what's it called? 1.04. Then the third odd ratio here, we have 3.09 raised to the power of -4. So the first one here is for the intercept, and then yes, it's for the horsepower, and then they have what we have 3 point this for the weight. How do you interpret your odd ratio? You are going to take one out of the two as reference. What did I mean by that? If it is manual that you want to take as reference, it's going to be what is going to be we have the odd of 1.04 times, we have what the odd of 1.04 of you using the horsepower in manual. Sorry, if it is manual that we use as reference. So we're going to base our conclusion on automatic. So we have 1.04 times using automatic, people using automatic compared to manual. or the horsepower of the automatic compared to manual. So when you are doing your logistic regression, you have to take one as reference. I think here our 0 here is automatic. So we take automatic as reference, then we base our interpretation on what on manual. You can still read further on the odd ratio. So let us check what we call the logistic regression model evaluation. We want to evaluate what's it called? Our model. So control R, control R, control R. Okay. Let me check. Where's the table? Okay. Now, if you look at this, remember that I told us that what's it called? Confusion matrix. If you look at this confusion matrix, this is we have 0, 1, like 2 by 2 table. We have 0, 1, we have 0, 1. This is the predicted value that the model predict. Then this is the actual value. So now, if you look at this, please, if you arrange this very well, so we're going to have how many rows that we're going to have now? 1, 2, 3 rows. Sorry, we're going to have 2 rows. So 0 and 1. But this prediction will come. How will I put it? There's no pen on this. I would have just loved to write. So what I'm trying to say here is that out of this data set, your model correctly predict they correctly predict 18, but wrongly predict 1. That is it. Look at this 18. This is the prediction. Prediction are this 18, 1, what's it called? 1 and 12. Are we together now? So everywhere you are having 0, 0. 0, 0 means correct prediction. But when you have 0, 1, that is wrong prediction. So here the predicted value is 18. And then under was 0 and 0. 0 under the actual, 0 under the predicted. But the value he predicted 18 correctly. But if you come to under actual, we have 1 here and then we have 0 here. So he predicted just 1 incorrect. So now if you come back to under what? Under the 1 and 0. So that means that he predicted this one wrongly, and then 1 1 he predicted it positive. So that is why we normally, that's another way that we normally check our model, by using a confusion matrix. Then another way that we can use is to check the receiver curve. So then we have what? Let us plot the receiver curve and let us see how it behaves. Oh, did I need any package? Let me see. Okay. This is the, why is it so small? This is our graph. And then the value of the area under the curve, AUC, area under the curve is 0.9838, which is the same as 98.38. So that means that your model is 98.38% what's it called? Accurate. So that means that what he predicted is 98.38 accurate. So that means that this is still okay. Now, after you've checked this your model, so you can now use this model to make prediction. So this is the and then the what's it called? The specificity is that okay, this is negative and it predicts it as negative. Oh, this is positive and it predicts it as positive. So, but the area under the curve is very, very important. It's very, very important. So the percentage is going to tell us the percentage of the what? Of the predictor. So now let's move on to time series analysis. Now in time series analysis, we want to use the data called year passenger. So let me run it. Control R. Control R. So this is, I want to print the data so that we can see it. If you look at this data, hello, can you still hear me?
Yes, sir.
Yes, sir.
Okay. Okay, Avik, what is standard or cutoff of AIC? Okay, okay. Okay. I'm good. If you look at this December, then what is the year? The year is 19, that from 1949 to 1960. So this particular year, they observe the passenger boarding year for 1998 January for the year 1949 up to the 1960. That is the data that I want to use. Remember, the first thing you have to plot it, and let us see. This is the plotting. Why is this not showing very well? Okay, this is the plotting here. So if you look at this plot, I'm trying to zoom this. Okay, if you look at this plot, you will discover that there is an increase, the upward increase. This is 1950. There is an increase when we get to 1950, then it's continue like that. So this particular data is telling us that over the year there is an increase in the year passenger that they have. Now let us decompose it so that we can check some other things there. Look at this decomposition. I want to zoom this. Oh, sorry. Okay, good. Look at this decomposition now. I was able to decompose it. Look at the trend. Look at the trend over the year. There is an increase in trend. Look at it. This is the trend. Then look at the initial observation is this that we plotted. Then we have the trend. Then this is the season. This is the season. It's going up, coming down, going up, coming down, going up, coming down, going up, coming. This is the behavior of the season. And then this is the random effect, like the cycling. So by the time you do the decomposition, from there, maybe it's only trend that you want to check. You can quickly bring out the trend and explain, oh, over the year, there is an upward trend in the year passenger. So that means that every year, the rate at which people are taking flight is what is increasing, is increasing, is increasing. So this is the trend to do what? To check that. So now the next thing is only graph cannot tell you whether the data is stationary or not. So, but we also use what we call the stationary using the augmented Dickey-Fuller test. So by the time you want to use the augmented Dickey-Fuller test, we're going to install the package called T-Series because it is the time series that we want to use. So once you do that, Control R, then we use the ADF test. That is how we normally carry out the augmented Dickey-Fuller test. ADF dot test. So Control R. If you look at the result here, let me expand this so that we can see. If you look at the result here, we have the value for the augmented Dickey-Fuller. The p-value is 0.01. How do we count this? Now, in augmented Dickey-Fuller, the known hypothesis is that the data is not stationary. Is not stationary. Now, the alternative hypothesis is that the data is stationary. Now, if you look at your p-value here, the p-value is 0.01, which is less than the alpha value, which is 0.05. So that means that we are going to reject the non-hypothesis and conclude that the data is what is stationary. So that means that this data that we are using is stationary. So what if it is not? Then we use the word difference with different. That is when we're talking about the backward difference the other time. So how do we do that? We use what we call diff of that data. So it is going to differentiate that data. So let us difference it. We are almost through. Once we difference that data, okay, let me check the value that we have. Now, if you look at this value now, let me increase this so that we can see. Remember that initially when we call in our data, we have values here, big value. But now after difference, Look at those values that we have. Look at those values that we have. So immediately you difference it, then you do what? You will check for your, what's it called? Your augmented decifula to check whether the data is stationary. But if the data is not stationary, you are still going to difference it again. That is why we have difference of order 1. That means that you are differencing it just 1. Difference of order 2. That means that you are differencing it 2 times. But in time series language, we have the lag 1, lag 2. So when you're saying the lag 1, lag 2, one by 1, 2, 3, 4, 5. So, but in our normal language, we normally use difference. So now, immediately you difference it first time, you check the stationarity. If it is not stationary again, you are still going to difference it again. So immediately you do that and you have your stationarity. So that means that you are going to use it like that for what? For building your model for forecasting. Let me plot the graph. So this is now the graph for the one that with difference. Now, how do we use it to forecast? How do we use it to forecast? Now we are going to install another package called install what's it called? Forecast. I think I've installed that. Let me call it out of my library. So now the model is auto.arima model. I want to use this particular ARIMA model. ARIMA here simply means that auto regressive integrated moving average. So what I'm telling the ARIMA to do is that fits this model automatically. That's why we have auto.arima. So by the time I do that, run this, then let me have the model summary. Look at this model summary. So now this is my model summary. Now this one is we have what's it called? We have 2 here, ARIMA 211. What is the meaning of this? ARIMA 211 is the model. What did they mean by that? This one means that it is it performed the, what was it called? The, how will I put it so that I don't want to use statistical term here. I don't want to use statistical term at all. So that means that the D that you're having here, the 2 that you're having here is for the autoregressive. So the autoregressive here is 2. That means that it moves like 2 times for the data. It moves 2 times backward for the data. Then it integrates it 1. That is the meaning of this R. I that you are seeing here means integration. So 1 means that it integrates is just 1. Then the moving average, it moves 1, just 1. You can have ARIMA 311. You can have ARIMA 321. So in this case, if you are doing this yourself, the reason why I put auto is that it's going to look for it himself and fits the one that is okay. If I'm doing it manually myself, I can first of all find what is ARIMA 111. Once I find the ARIMA 111, I'm going to check for the AIC. Once I will still move again to find ARIMA 112. So I'll keep on doing that. But there's a way in out that you can give out instruction that I don't want to be doing all those problems. Fix it for me. Check the one that is okay out of those ARIMA model. If you look at this now, we have our AIC, the Kaike information criteria to be what? To be 101. We have 1017 point this. We have the AIC correlation. The AIC correlation to be this. Then we now have what we call the BIC. But the AIC and the BIC here that we normally use. So the AIC correlation, we don't normally reckon to it because most of the value of the AIC correlation are always greater than the normal AIC. So now, then we have what we call other metrics. We have the means, what's it called? The mean error. We have the root mean square. We have all those ones that we've mentioned. So we have this. So this is how we are going to come to the forecasting, and then you will write the, what's it called? The interpretation of this. Let me take the question that we have in our chat box. Let me take the question that we have. Okay, what is the standard or cutoff of AIC? Actually, the AIC, we use it to compare models. When you have 2 or 3 models that you want to check, so we only check their values in comparing it. But maybe I have to check for the standard, but I don't know the standard for now. But because the one I've been doing so far, I normally compare 2 or 3 models, and immediately I discovered that the one model is higher in terms of the AIC. One AIC is higher in one model compared to the second one. I will just make conclusion that this particular model is better compared to the second one. But I've not checked. To the best of my knowledge, I have not checked whether there is a standard cutoff for the AIC. So I'm going to do that. So please, any question, please? Any question? Any question? Can you still hear me? Are we still there?
Yes, I have a question.
Please go ahead.
Yes, we can hear you. So from the last one you just did now, this forecasting, assuming we were actually looking at something, what would be the interpretation now? Assuming we're looking into the future for something, what would possibly be the interpretation for the analysis you just did now?
Okay.
Don't know if you understand the question.
I get. Now, what we just did now is this. Based on the past, what's it called? Based on the past data that we have developed a model called ARIMA 211. That is the model that we just developed, ARIMA 211. So the essence of this ARIMA 211 is that give me any data. I've trained my model with the past data. Now give me any data of the passenger. I can use it to predict what will happen in the next 4 years. So the essence of us developing a model is for the prediction. Any model that you cannot use to predict, it is useless. It is useless. So what we just demonstrated tonight is that we build up a model. Although it's not that deep, but at least for a start, we build up a model in time series called ARIMA 211. So the ARIMA 211 is the model that you can use to predict the year back. Let's say for your own field, you want to develop a model to predict, or let's say, the progress of a particular disease. So after you've collected your data for over years for that disease, then you can bring that data into this time series. The only thing that you're going to replace here is that with the same code, you are going to just replace anywhere you are seeing the year passenger, replace it with that your data. So from there, when you plot your data, you are going to check the trend, the pattern of that your data. So after checking the pattern of that your data, you can decompose it to actually have the trend. So from there now, you are going to check whether that your data is stationary by using the augmented Dickey-Fuller test. So immediately you confirm that your data is not stationary. So that means that you are going to differences. You are going to difference it. So once you difference it for the first time, and you still use the augmented Dickey-Fuller to check for the stationarity, and you still discover that it is not stationary, you are still going to difference it again until you attain a stationarity before you can use your data to build a model. So immediately you attain that stationarity, then you can use Autodot's ARIMA to fit that your model. So immediately you now have the model. It is that model that you can now use to predict that disease progression. So that is the essence of with developing the model.
Thank you, sir.
You are welcome, ma. So any other question? Where's Mr. Lydia and Co? They've left. Okay. So we want to appreciate everyone. So we've come to the end of this training. So we started December last year, and here we are, to the glory of God. Then starting another training next month. So that one is going to start February. That one is going to start by February 4, and it's going to run for a month. And this particular training that we just conclude now is coming up again, the batch B of it. For those people that maybe you have a friend that you want that person to join, or you have someone that is in need of the what's it called, analytical skill or the statistical skill. You want to know how to use this our statistical software, how to perform data analysis, how do you conduct research, how do you do the analysis in research, and some other things like that. So another batch is coming up by March. So it's going to start from March 14. So we have the timetable drawn already. Also, then lastly, we're going to send a Google link to like a Google form to what's it called, to our group. So in that Google form, you are going to correctly fill it, so that the name that is on it will be the name on the certificate of participation that we are going to give. And also, we want us to help us answer some questions that we have there, just for us to do better in our subsequent training. So, in the absence of no question, or do we have any question? In the absence of no question, this is where we are going to call it end of this gateway scam. Okay, Mr. Lade, you are still around. Please go ahead. Mr. Lade? Okay. So
Okay, sir. So, although my question is, I don't know whether you love to stop the recording first, so that because it's not, you know.
okay. Let me stop the recording. Oh, okay, recording stopped. Let me stop the streaming online. But we see how people at YouTube. Oh, I hope your question is not something that they can gain from. If it is something that they can gain from, so let me leave it, let them hear. Because we see how people watching at YouTube. What do you think, Mr. Ide? Are you still with me?
Okay, sir.
Okay.
I'm with you, sir. I didn't know that I've muted. Okay.
Okay.
The one for YouTube, is it? I thought it's anything one puts on YouTube will be there till the person decides to remove it. Is there a time frame? Because I think you said it will be there for a whole year. Is there a time frame for content put on YouTube?
Yes. No, it's not that. No, 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 no. You know, but the one that we are putting there, you know, in YouTube we have like three. We have the unlisted. This one that you are we are streaming online now is only those people that pay for this class that can see it.
Oh,
There is one
really?
of Yes, there is one of public. So the one of public, anybody can see it. If they search for it, they can see it anywhere. But the one that is called unlisted is only those people that you want to see it that they will see it. Then there's one of private too. So it is unlisted, and then the unlisted is
Oh,
not counting. Here you get. So anybody viewing it is to my own benefit, not the YouTube benefit. I don't really get what I'm trying to say. So I'm going to leave it there for a year before we move it out.
oh, okay. I was assuming if I search for Joe Emmanuel, I would see
If you
all
start, you
the.
will see me there, but you will not see this lecture there because it's on the I put it on list
Oh,
on list. So it's not general.
so does that
It's
mean
not
that
general.
only the people with the email that you recommend will be able to check it? Or
Yes, these are the people that are paid. So what we
eh,
are going to do, we are going to compile all those classes. We are going to compile the links. Then we are going to send the link. Then your email that you want to be using to access it, you will fill it in that form. So it is those email that we're going to
okay.
register. Only those email that can access it. Did you
Oh,
get it? So peradventure, if they share it with anybody, they cannot access it. So that by
oh,
doing
ah,
that, so that it
I
will be
didn't.
that it's something that you paid for that you are gaining. So that anybody cannot just come and they start watching it without payment. Did you get it, please?
Oh, yeah, I got. I didn't know YouTube has that feature. I thought if I
Yes.
just search for your name on YouTube, every of your content, will show. I don't know that it's
So, like the one we treated on Wednesday, the one of Wednesday is public. Anybody can see it. The one of Wednesday is public. Anybody can see it. But this one that we are doing is private. Is private. So it's not everybody that can see it. So
So
it's going
I
to
will
be
you
there.
not be able to. Okay, yeah,
Oh yeah,
okay,
ask your
sir.
question.
I'm with you. I will you not be able to give you more watching hours. I think
Uh,
I don't know.
the one actually, I'm still going to do some the one that is going to be public. At least I have some video there that people are still watching, and I'm getting my watching hour. So, but this one is something that I still want to work on, build on, and there is a course that I can put on all these Udemy and Coursera and co that people can be buying and be watching. So I don't want to
Yeah.
put it public yet.
Okay, because I
So I
think
have
from even apart from apart from putting it there, I think when it comes to YouTube monetization, for you personally now,
yeah, I
I
understand.
think the number of watch hours ahead, I think
And
whether they
the
call it
number
CPA
of
or
hour,
something, I don't
yes,
know.
the number of watch hour and then some other things. But for now, I still want to focus on how to use my skill to make cool money first before we start looking at it, YouTube monetization. But I have videos there that people watch. Like my calculator now is my calculator that is taking the lead. How to use calculator to compute p-value. So it's taking lead now. It's very short, and people are even people from outside they are watching it. So and the hours is counting. So no problem.
Okay.
Thank you so much.
Yeah.
Thank you so
Also,
much.
when it comes to, I think Facebook is connected to Instagram. So anything activity on Facebook can now Google Meet. This is Google Meet. It's owned by Google and YouTube. They are two different owners. So how were you able to live stream, from directly, direct live stream from YouTube,
Okay.
from
So
Google Meet directly to YouTube? So far, they are owned by different persons.
uh, we paid though. This one that we are using is a paid. So once you paid for it, there are other features that comes with it. So all the one that I've been all the software Google Meet I'm using is a paid one. So it's a paid Google Meet. So that is why I can take as long hours as I can. I can record. I can link it to YouTube. I can. So it's a paid one. So that's why it's not free. You can't do all this thing free.
Okay, so if, for instance, if you pick the option of Zoom now, so Zoom 2 can also live
Yes.
stream directly to
Yes. Once
to
it is paid, Zoom. Yes. Once it is paid, Zoom.
because
Once
I
it
was
is
assuming that is why you decided to pick Google Meet instead of
no no
Zoom
no
so
no
that
no
it
no
would
no
be able to.
no no. It's the same. It's just that Zoom, the amount as Otitobi. So the amount that they charge when I do the conversion to Naira, Naira is crying. Naira is crying. So and then how much did I even charge? So I also consider other factors. Also consider other
So
factors.
so is it per hour that
It's
sorry,
monthly
I
sub-
don't
it's monthly.
I think it well, I think it's personal question that you so that's why I say you should stop the recording for. I don't know whether other people will also be learning to, but I just
No
okay, so
problem.
it's monthly. So one can take any number of hours as possible, even if it is 4 hours per lecture for
Yes.
different period of the day.
It's 24 hours. It's 24 hours.
Okay, 24 hours for the whole month.
Yes, 24 hours, 24 hours, 24 hours. You can be doing it every day. So
Oh,
24
okay,
hours.
okay.
So for a month, 24 hours, and you can record it. So that's it. It's not
Oh,
40 minutes. If it is 40 minutes now, they will have thrown us out since and still log in again. So it's not 40
oh,
subscription. I subscribe for that.
okay, okay. So is the different the last one because of other people? Is the difference between the Zoom and Google Meet, is it that wide? Oh.
It's wide though. By the time you do the dollar conversion, you will know that it's wide. By the time you do the dollar
Like
conversion, you know that it's wide.
like how much dollar difference?
Ah, okay. I can't answer that one now because I don't know the current rate. Because the last time I checked was I think last year when I wanted to start. So I checked it and I discovered that I don't have that money for Zoom. But once I start with Zoom now and tomorrow you now see me with Google, you'll be asking me a question. You used Zoom yesterday, you use Google tomorrow. You are not consistent. So let me stay with Google. So and I'm enjoying it.
Yeah, yeah. I mean, like, how much is what's the different dollar difference in the what's the differences
Well, I think
in
it's
the
let me just say it's like maybe $20 or $25 different.
that's really that's really something.
So that is just the difference. So
Okay, so let me allow others to
okay.
ask.
Oh, Madam Ibong, can you ask your question?
Okay. Yeah. Yes, thank you very much, sir.
Yes,
At
ma'am.
least this is an eye opener. So please, I when you were responding to Mr. Laide, you made mention of compiling all the links and then you send it to our mail. Please, will it be this Google Meet link or it will be the YouTube link? Because
It's
I noticed
YouTube.
if I want to, okay, what
It's
I'm
YouTube.
asking is that anytime I try to rewatch the session, um, the YouTube is not really clear. So that's why most times I prefer this Google than the
Um,
YouTube.
you have to check your network. You have to check your network and make sure you are in a place that is okay. The problem with Google is that there is this particular course 727 I normally take, and then I normally put it on my Google Drive so that people go there to watch. But it got to a time that Google did not allow them to watch again because that place is not designed for them to be watching. It is YouTube, so they didn't have that capacity for people to be watching and be downloading. So that was the problem. It was like 2 or 3 days to that exam, so I just have to move all those video to YouTube. So since then, I don't leave video on Google Drive again. I put everything on YouTube, and people are watching it there. So you can check your network for the clarity and then the sound and everything is network. So it is the
Uh,
same thing that you're going to see in Google that you're going to see on YouTube.
so I think I experienced the same thing too from my own end. It's not really clear. It's not really as clear as, this live stream is very clear. We can see all the numbers, all the screen. You can see the screen very clearly. The numbers on the screen you can see clearly. Even the one we don't see clearly. Even if we zoom, we see very clearly. But the other one, the other replay, it will look fuzzy. It's so blurry. So I think I get what she's trying to say. The other one is blurry, kind of, and it's a computer screen, so and the letters are small, so it's kind of a bit difficult.
Okay, I'm going to check that because I have some people on YouTube now that they are watching it, and if they experience that, they will have sent message since. But I'm still going to check it myself because every video of the lectures that I give out, I will listen to it again and check it. So I'm still going to check the one of tonight so that I can see that. So I'm going to check it. Madam Titi, Madam Titi Layo.
Good evening, sir. Good evening,
Good
sir.
evening. Yes, ma'am.
I just wanted to state that the YouTube that you were talking about, the last time I joined YouTube too, there was a time I didn't join this Google Meet on time. The thing it wasn't clear. The numberings were not clear. So I guess maybe that was why the recordings, but the ones I've seen so far, they were clear to me. So I really don't know if others were not clear.
Okay. We're going to check that. We're going to check that. We're going to check that. So please, any other question? Any other question, please? Yeah.
So I have a question.
Please go ahead.
Please go ahead. Yes, I just wanted to ask that are there opportunities from your end for maybe those of us who took this course who are interested or willing to like maybe convert the little knowledge we know into a source of income? Maybe you have some tax or something that you want to outsource and we can start beginning from there little by little.
Oh, yes.
Oh, yes.
Please mute your
Please
mic.
mute your mic.
I don't know, maybe you normally check my status, but I think after this class, I'll be putting those opportunities on our group. I have people from different field that I receive message from Ujo, can you do this? Or but help us find someone that can do this. Help us find. It's not everything that I do. Let me just say it now. It's not everything. So and then some things that I even know, time did not permit me. So I used to give it out. I put it on my WhatsApp group, sorry, on my WhatsApp status, and people will message me. And I will tell them, show me the work that you've done before, so that I'm the one recommending you. So that if anything happen, They will not come and meet you again. They will say, oh, it is Ojo that recommended you to us. So they will come and meet me there. And I hope you should be the one to do the work for us and the like. So there are a lot of opportunities. So I'm going to be dropping it on that group. Or let's say starting from tonight, I'm going to be dropping it. When I'm seeing it, I'm going to be dropping it. So
All
there are a
right,
lot
sir.
of
Thank you.
all right, no problem. Thank you so much. So any other question? Okay. In the
In
absence
the
of
absence
none,
of none.
Okay, the last one is not a question actually. Can you hear me, sir?
I can hear
I can
you.
hear you.
Yes, it's not a question actually. So I just wanted to thank you for the training sessions. Although on my end, it's not as if I understand a lot of things, but since there is opportunity for me to rewatch it, I just wanted to commend your teaching style, like for you in particular. Thank you very much for taking out your time. The patience and the ease with which you teach is very, very admirable. So well done, San. More of God's grace to you.
All right, so thank you so much. I appreciate that. So please, I don't know, maybe you can help me put that in typing. That would be some of our remark. So I would really love that so that if I'm telling people about our next training, I should be able to have evidence from the past participants. And I would love the recommendation from your side, a good recommendation from your side. And then if you see any other thing that you think that we can still do to improve our teaching method and then to improve how people will learn and the likes, feel free to tell us. Thank you so much. Uh, I wish you all the best in your journey of life and then your research.
Thank you so much.
Thank you so much. Night. So thank you. Good night.